Welcome, all of you here. Welcome, online audience, because today is a very, very special chai and wine. Now, through all these years, you would have noticed that it's very rare that somebody who's not from TIFR gives a chai and wine presentation or is at a chai and wine session. But we are delighted to have somebody who has a very, very close link to TIFR and happens to be visiting just at the right time. Please join me in welcoming Professor Atish Dabholkar, who is the director of the International Centre for Theoretical Physics, ICTP, at Trieste in Italy, and a renowned scientist in many ways. So he is both one of the leaders in work on black holes and quantum entropy of black holes, etc. But he also straddles what you see as the title of the Chai and Why, the public understanding of science, and a very, very strong feeling that science isn't something which is limited to just a research lab or even a textbook in school, but science is a way of exploring the world and of asking questions and of engaging with society at large. And that's what he's going to tell us about today. But before that, for anyone who's coming for the first time, Chai and Why happens always on the first Sunday of the month at 11 o'clock at Prithvi Theatre, on the third Sunday of the month at Ruparel College in Mumbai. And if a month is a fifth Sunday like this month, we will be live from a lab in TIFR. Just to tell you, next month's session, a month from today over here, we will be looking at the world of chemistry, where Professor Ankuna Datta from TIFR will come and speak about something. But more about Atish. Atish, of course, started his career in science at IIT Kanpur, from where he went to Princeton, did a PhD, did the usual postdoc stints at places like Rutgers, Harvard, Caltech. But eventually, we were very, very lucky that he came back to TIFR and joined the Department of Theoretical Physics. And he was there for probably 10 years or something of that sort. After which he went, just before the COVID pandemic, he went to the ICTP as its director. And we are very proud that he is here today and he is able to tell us about this chai. Now, yesterday was National Science Day. So this is very, very timely to speak about scientific temper and the public understanding of science. And over to you, Atish.
Okay, thank you very much.
So just remember, online audience, we cannot see you. So the only way we can get your questions is via the chat. So please enter your questions on the chat. I'll be monitoring the chat and we'll either take them at the end of the talk, or if it's really important, I will interrupt Atish and ask him the question. Same here, if you have a quick clarification, please ask. If it's something that's a longer discussion, you have all the time in the world. You've come here, you get a lot extra, you get chai and you get time for discussions. Online audience, no chai for you. Make your own chai. Okay, on that note, over to you. Now you can start sharing.
Okay. So first of all, thank you very much, Arnav, for giving me this opportunity. It just so happened that on this, it has to be the fourth Sunday of the month, and I happen to be here, and it has to be the 28th of February, and I happen to be here. So he really made me work last 2 days.
Yeah, Atish gave the national the Science Day talk yesterday, and that also you can watch on YouTube there.
So also thanks for this opportunity to speak at this iconic Prithvi Theatre. It's my stint as a stage actor. So I want to tell you about black holes or unification, actually starting with the idea of unification, why many scientists around the world are working on it. Just get rid of that, okay? Oh, just you are actually you have to go to Zoom. No. Yeah, Zoom. Go to the Zoom window.
Not coming online, but might be bothering people. Yeah, I think let it. Well, it's it's not coming on YouTube, but it's coming. Probably just click on opening.
Yeah, but we don't see the screen there. It's a weird. I'm not able to move forward now.
Yeah, you need to switch back to this one.
You need to
You've got this multiple windows thing.
Now I lost the mouse. Yeah. I don't see the.
Oh, actually, his cursor is not there.
Cursor is not seen. This. Skip.
Please bear with us for a minute.
Technical. No, it's not. Okay, but in the meantime, I can talk. You can see me.
I don't see cursor on the screen.
You see the cursor on the screen. That's the thing. This cursor has gone to the screen. Okay.
Okay, done.
Now it's not moving back and forth. We need to go to the window, I think.
Now I have only half the window.
Yeah. You know this.
I have no idea of that.
I also, somehow it's behaving in a manner that I'm not used to.
Let's restart the screen.
Maybe that's not a good idea. Now it's good.
Okay, good.
Okay. So today I want to tell you about some of the exciting work that has been done in what is known as unification. So I want to explain what is unification, why it is so exciting, really bringing it up to a point where it connects to my own research. Then I'm going to switch gears. I'm going to tell you a bit about science and society, in a way, the connection between the two. I will mention a bit about some work of the Abdus-Salam International Centre in this context. And I will tell you a bit about the International Centre for Theoretical Physics, where I work, where I'm currently the director, which also is in a way related to making science globally available as the mission. So let's start with unification. Okay, we all use a mobile phone, all of you, and it uses some very amazing equations written more than 150 years ago. So it's a good idea to know what they are. And it came from the effort to understand electricity and magnetism together. To join electricity and magnetism. This is electricity, this is magnetism. They don't look anything like each other. But even though they are drastically different physical phenomena, they are actually turn out to be the two sides of the same coin. Diverse manifestation of a single whole, which is joined together at some fundamental level. And that's what we mean by unification. Something which looks different, it's like a trinity, but they are actually the same entity. And this you can call as electromagnetic unification. So you have electric charge, which causes the electric field, electricity. If you have a charge moving, then it is a current. And the current produces magnetic field going around the wire. So magnetism is like electricity in motion. This is what people understood, especially Maxwell. And he wrote these very beautiful equations where F is like the electric field and the magnetic field combined into a single entity. You can write this in two lines, very simple equations, and J is the current. These are known as the Maxwell's equations. And everything that you do with electricity and magnetism today, what is in your mobile phone, satellite communication, X-rays, IWC, is based on these equations. So this led to something even more surprising, unification of electricity, magnetism, and light. So they are actually three sides of the same coin. This is electricity, this is magnetism. But Maxwell's equation had a wave-like solution. It's like a wave. Magnetic field is oscillating this way, electric field is oscillating that way. The wave is going in one direction. And depending on how long is the wave or short is the wave, you can basically describe the entire spectrum of light in terms of these waves. this is really spectacular. And then amazingly, he got the speed of light from phenomena having to do with electricity and magnetism. So really getting the speed of light out of nothing, out of electricity and magnetism. Light, but then we realize X-rays, radio waves, microwave, everything is just an electromagnetic wave. It can be very long wavelength or very small wavelength. And that's all is different. So this immense diversity of phenomena is combined in these two simple equations that Maxwell wrote. But we know that you might have heard about photons and lasers. Light is actually quantum. Light looks like a wave, but it's actually made up of, it also behaves sometimes like a particle. And that quantum is known as a photon. And what we see, Maxwell's equations are an approximation to a more complete theory, which is valid only when the number of photons is large. When you have large number of photons, it looks like a wave. That is known as quantum electrodynamics. And to give you an idea, the theory of quantum electrodynamics agrees with experiment 1 part in a trillion. Just look at it. How many digits you have to go before you can even see any difference. So you calculate something on a piece of paper using some equations. Then you go to a lab and you do these very complicated experiments. And you find that you get exactly the same answer. And this is a very remarkable power of theoretical physics. And just by doing some calculation in your laboratory, in your office, you find something that agrees with it. But now Rutherford discovered that actually inside an atom there is a nucleus. You all have studied this in school, that inside an atom there is a nucleus. Nucleus is made up of, in terms of protons and neutrons, and the electrons are going around it. So this kind of a picture actually emerged when Rutherford did a very simple experiment. He took a gold foil and hit it with some alpha particles coming out of some radioactive source. And that actually revealed him the structure of the atom. That there is something, because what he saw is like throwing a ball at something, and if there is something hard, it will come back. He was very surprised that something was coming back at him as if it is hitting something hard. And that's how he concluded that there must be a nucleus. And this method is a method how we understand physics at short distances. It's a very, at some level, stupid method. It's like, suppose you want to learn about how cars are made of. You take two cars and you bang them against each other. You will see a steering wheel will come flying out. And that you conclude that, the car is made up of a steering wheel, the car is made up of a tire. This is the kind of a method that we follow even today. This is the biggest accelerator in the world. They're several kilometers long, where you basically bang two elementary particles against each other. And to detect, there is a human being over here. This is a detector. This is not an accelerator. This is where you detect how the particles are coming in. So this is the kind of experimentation that we're able to do and find really precise agreement with experiment. But now the question becomes, what principles govern these new forces? Right? We had electricity and magnetism. So far, you are with me. And some famous physicists like Freeman Dyson said, the correct theory will not be found for another 100 years. No, it's too complicated. The nucleus is too complicated. And he was quite spectacularly wrong. Within a decade or two, there's a new principle called the gauge principle. And these are known as SUN quantum gauge theory. So don't be scared by this name. I will explain what it means. So this I would call unification of principle. These are totally different phenomena. They are somehow governed by the same principle, and that principle is the gauge principle. And that principle is actually simple to state. So basically, you remember in Maxwell's equation, you had one field, F, which is basically telling you what is electricity and magnetism, and one kind of charge. It can be +1, -1. Electrons have negative charge, protons have positive charge. But there is only one kind of charge. Now you can try to generalize it. What if there are two kinds of charges? Up charge and a down charge. The up can be plus or minus, down can be plus or minus. So there is more variety of possibilities. But then it turns out your field has to be a 2x2 matrix. It's like an arrangement of 4 numbers. If you have 2 charges. Now you can generalize 3 charges, and 3 by 3 matrix. Now, this looks like a fairly, almost a childish generalization, but actually it turns out this is a very fundamental principle. And in fact, all the known, and this is named by 1, 2, 3 basically, U1, SU2, SU3, you can do SUN, N by N. And this describes electromagnetic dynamics, as I've told you. But this turns out that this simple generalization describes the weak interactions, weak nuclear force exactly. And the equations, very similar to Maxwell's equations, describe the strong nuclear force exactly. So this shows a kind of a power of the human mind, that we generalize something sitting in the laboratory, in your office. Instead of taking one charge, we take 2 charges. It looks like we are generalizing. But that generalization is actually reflected in nature. So could the weak nuclear force be joined together with the electromagnetic force? Can you now do this unification even further? Again, a very eminent physicist, Wolfgang Pauli, one of the creators of quantum mechanics, said that let no man join together what God hath torn asunder. Okay, this is a joke. And when people get married in a church, the priest says that let no man tear asunder, separate this couple, what God hath put together. So Pauli sort of made a joke on this, but this turned out to be more clever than wise, because he was again spectacularly wrong. In fact, the founding director of the ICTP, Abdus-Salam, was actually exchanging with Pauli, and Pauli basically said, don't waste your time doing this. But good for Salam, he actually continued to waste his time. And this electro-weak unification was taken. So now look, we have come very far, starting with electricity, magnetism, light, and weak nuclear force, which is responsible for radioactive decay. All can be described in a single framework. So that's the power. With writing some simple equations, now you can understand everything that is happening in the universe. And there are many new ingredients, spontaneous symmetry making, new particles, massive vector bosons, Higgs boson. The Nobel Prize was given in 1979 to Bilasha. This is Abdus-Salam and Weidner. These people got the Nobel Prize for this. Okay, so far, are you with me? He's going to ask me questions when it comes to black holes. But now let me give an analogy of what is the idea of unification. It's a bit like you have a beautiful temple of electromagnetism where you worship the deity of electromagnetism. There is another beautiful temple of weak nuclear interaction. There is another deity of the weak nuclear force. One day, somebody doing some excavation finds out there is actually a secret pathway that connects to these temples. And they are actually part of the same temple complex. You know, this is for, I think this is for Madurai. And you are actually worshipping the same deity. You thought that you were worshipping different deities, but actually you are worshipping the same deity. That's the idea of unification. And now our understanding of nature has progressed so much that just with this table, you can describe basically everything in the world, from your mobile phone, from what is happening inside a star, what is happening, nuclear reactions, what is happening inside a nucleus, how does atoms move, quantum computers, semiconductors. It comes from just these few particles, upward, downward, these are called leptons, neutrinos, and there is a photon, graviton, and some massive vector bosons, W and Z. So in terms of very simple elements, so this is really truly atomic theory, right? Atomic theory means everything is described in terms of some fundamental atoms. But what is amazing is that all our perceptions, you know, this color of the shirt, is all coming by just interactions between these particles. Deep inside my shirt, there are electrons and protons. In the air, there are various particles going around. What I'm talking to you, the sound is being propagated. So the light that is coming out, it's all interactions of different particles. And if you stop to think about it, it's really quite a spectacular achievement of the human mind. That just, there was no reason why nature had to be so organized. And there is this famous Higgs boson you might have heard about. That's a new ingredient that you know. But we have left something very important. You would agree Because all of you in school, first thing you learn about forces is the force of gravity, right? Goes back to Newton. Newton's law of gravitation predicts planetary motion in great details. So the question is, all very nice, everything that is in the room we can describe, but what about the planetary motion, right? That's what planetary motion, how does it fit in the scheme of things? Can the force of gravity be unified with other forces? That's the question that that's the question that you should ask. Newton did this well before electricity and magnetism, 300 years ago. He didn't know about electricity and magnetism. Now we need to ask this question. But before that, we need to do another unification of space and time. Okay, now you might say this sounds crazy. What does it mean, unification of space and time? So time is something that your watch measures. Space is how much distance I'm going this way. I can go in 3 different directions. There are 3 directions I can go in, and time. There are 4 directions that way. But they have absolutely nothing to do with each other. But Einstein famously did this unification of space and time. And the key ingredient is actually simple to explain. Key ingredient is that time is relative. That's why the word comes, relativity of time. See, when Newton was doing his physics, he believed that my clock and the clock of somebody sitting on a train shows the same time. They are in sync. They do not show, it does not depend, it's not relative. Time is absolute. Time is something that is defined for everybody, in the same way, whether you're in motion or you're not in motion. But Einstein said, no, moving clocks run slower. Okay, now this sounds crazy. That means your clock will show 4 minutes if you're moving in a very fast rocket ship, when my clock shows 5 minutes, 5 seconds. 5 seconds, 4 seconds. How is that possible? So here is a very nice video that illustrates this. And this is possible because speed of light is actually constant in all frames. Okay, this is a property that is quite shocking in a way. Because you see, if you have a throw ball, if you start moving on a motorcycle at the same speed as the ball, then the ball will look to you that it is at rest and you can catch the ball. Whereas to you, if you're standing here, the ball will look like it is moving. So the speed of the ball actually depends on whether you're moving or not moving. That's not true for speed of light. For some reason, speed of light is the same, 300,000 kilometers per second in every frame. Now, just a fact of life, okay? So then Einstein said that let me use this fact to define a clock. How do I define a clock? I say that I send a beam of light up, a mirror, and it reflects back. When it returns, I say 1 second has passed, or 1 unit of time has passed. Okay? If you do that, just look at this video and you will understand relativity of time. And you can actually do a simple calculation. My son is like, when he was like 12, 13 years old, when he was studying Pythagoras theorem, I said, you can actually understand this. And look, there is a light clicking up and down, whereas this clock is moving and it is showing slower time. Why is it showing slower time? Because, yeah, somebody wanted to say. It's moving, but why is it showing? Correct. But the reason is very simple if you look at this, right? It has to travel much longer distance. And by using Pythagoras theorem, you can calculate how much distance it has to travel. And that what gives rise to what is known as the Lorentz transformation. And also E is equal to mc square. All that follows from this very simple observation. So Einstein just thought very carefully about how time and space, and now time and space are not independent because depending on your motion, time is changing and space is changing. Your time intervals and space intervals get mixed up between each other. So this led to a universal speed limit. Now it's like the speed limit on a highway. This is the speed limit across all universe, no matter where you are. It is 1 trillion meter per hour. Okay, which is the speed of light, 300,000 kilometers per second, roughly speaking. And nothing can travel faster than the speed of light. This is a consequence of Einstein's theory. Okay, for the simple reason, it's nothing very mysterious. If you sit down and if you know some basic algebra and college level 12th standard kind of physics, you can understand this very easily. And it has 2 dramatic consequences: gravity waves and black holes. Okay, now we are coming to black holes. Pay attention. His name is not Avyan. Avyan, pay attention. So my question to you is the following. If the sun disappears now, when will you come to know about it? Anybody wants to take a guess? Yes. Why? Huh? Light takes that much time. But Newton's law, do you remember Newton's law? Newton's law is that the force is equal to the mass of the sun times mass of the earth divided by the square of the distance between the two. So if you put mass is equal to, there is no time there. Is there any time in that equation? No. So that means if you put mass of the sun to be 0, the force goes to 0 immediately. There is no time. So Newton's laws would say, Newton would say immediately, Einstein would say, as you are saying, you are with Einstein. It's good. That it will take 8 minutes. But you see, you cannot have one law and doing is telling you one thing and another law telling you. That's why you need unification again. So this is unification of gravity and space-time. We had unified space and time. Now you want to unify gravity. Now what does it mean? Einstein realized that gravity is actually a curvature of space and time. Gravity is not a force in the usual sense. Now, what does it mean, curvature of space-time? It sounds very fancy. But let me explain to you what it means. See, suppose you are walking on the surface of the earth and you start at the Vishavruta, at the equator. Two people start walking north with their nose in front, straight. If you just were on a flat surface, you would just keep going and you will never meet. But on the surface of the earth, eventually they will meet each other at North Pole. They will say, wow, there must be some mysterious, this was destiny. There was a mysterious force between you and me. It's some mysterious force of attraction. And they will attribute it to some force. But actually there is no force. Just the curvature of space in which they are moving. So that's what is, so it looks like an attraction, but it is just a curvature. The fact that this space is curved. If space-time is curved, that mathematics is slightly more complicated. But basically the idea is this, okay? And that's called general relativity of time. It's called general relativity of time. It's about, it generalizes Newton's law of gravitation and it predicts gravity waves in black holes. So gravity waves, we have seen why it predicts gravity waves, right? Because it cannot, no influence can travel faster than the speed of light. So even gravity cannot travel faster than the maximum it can use is actually speed of light. And that's what it does. And that's called a gravity wave. Just like you have electromagnetic wave, you now have gravity waves. Okay. But what about black holes? Everybody wants to know about black holes, right? It looks very fancy thing. Yeah, scary also maybe. But it's not, again, a lot of these physics concepts are actually fundamentally simple to understand if you understand the problem. So what happens if I throw the ball up? It will come down or it will just, due to gravity. What if I throw it faster? But it will go further up. If I throw really fast, like at the speed of rocket, it will go to space, right? Yeah, so this is known as the escape velocity. Okay, it is roughly about 1 kilometer per second. Okay, so if you go as fast as 1 kilometer per second, it's like in a very fast jet plane, maybe 2-3 times faster than the speed of a normal aeroplane. That's how the rocket fast goes. Then you will not fall back. Or if you throw a ball like that, it will fall over there. Look here. If you throw it faster, it will go a bit further. If you really throw it fast, it will start going around. Right? Like a satellite does. The satellite keeps going around. This is how we launch a satellite. Just throw the satellite like that. Sometimes you throw it up and then you turn it. But basically the idea is there is something called escape velocity. And that depends on how much mass is there on Earth and what is the radius. If you not start making Earth very dense, like if you take the solar mass, sun Sun is 1,000,000 times bigger than Earth in terms of its weight. Now, if you squeeze it to the radius of the Earth, keep squeezing it to 3 kilometers. 3 kilometers is like smaller than Mumbai, right? Take all the mass in the sun and squeeze it to 3 kilometers, then you will get a black hole. Why? Because the escape velocity will become the speed of light. And what is Einstein's speed limit? Nothing can go faster than the speed of light. So if you cannot go faster than the speed of light, and if the escape velocity required is bigger than the speed of light, then you cannot escape. Then you have a big black hole. That's called a black hole. But even light cannot come out. Now, this sounded so crazy that Einstein actually himself didn't believe in it. Einstein actually wrote a wrong paper trying to prove that this consequence of his own theory cannot be correct. So it tells you that science progresses in this strange way. So a rocket can escape gravity if it's faster. I have explained this, and then you get a black. And physicists understand black hole in a more precise way. There's something called the event horizon. So I said 3 kilometers. So actually, that event horizon is nothing special. I mean, I could be walking through an event horizon right now, or you could be walking, but it's very special surface it's like a wall in space and time. It's a bit like you can enter, you came to my talk, suppose you get bored and you want to leave. If you are inside a black hole, you cannot leave. Once you came for my talk, you are there forever. Okay. So it's a one-way surface. Event horizon is a one-way surface. You can go inside, but you cannot come outside. And this is possible. So this is the artist's impression of a black hole. It's a one-way surface. Even light cannot escape. Now you might say that, so it took 50 years after Einstein didn't believe in it, a lot of scientists didn't believe in it. It took 50 years for people to start believing in the black hole. And it took 100 years after the equations were written down to actually detect a black hole in a very spectacular way. And I'm going to show you this video of two black holes merging 1 billion years ago. And then they produced so much energy because they basically merged into a big black hole, but whose mass was smaller than the sum of the two. So whatever remained was expelled in energy. And you know Einstein's formula, E is equal to mc squared. And look how large is c. C is the speed of light. So when you multiply the mass of the sun by c squared, you get enormous energy, which actually will be brighter than all the stars for a fraction of a second. But it's all in gravitational waves, so you don't see anything. But it will come and hit you 1 billion years later. And this is what people observe. Okay, this is a simulation. But these dots are stars. So as these black holes are merging and combining into one, the stars keep moving because the curvature of space and time is changing. So the light doesn't know what to do. It wants to come straight, but the black hole has moved. So the light also. So it looks like the stars are moving, but actually stars behind are not moving. Black holes are merging. They become into a big black hole. Okay. This is known as the LIGO experiment, laser interferometry. And India is actually going to become part of LIGO India. And in a few years, India will have this big telescope to measure gravitational waves, which will be a very important step for Indian science. So that brings us to the final question, unification, right? Everybody has been talking, we have been talking about unification. So we did electricity, magnetism, light, weak nuclear, strong nuclear, gravity. Now, how do we combine gravity? This is the problem which my generation is trying to understand. Unification is an inspiring guiding principle. Work of our Salam and others was a very important milestone. But the 20th century problem is to unify gravity, 21st century. But the problem is that the gravitons behave very differently than the photons. And the characteristic length where these things become relevant is so small, it's trillion times smaller than even the atomic nucleus. So you might wonder, how can you even say anything meaningful, without doing any experiment? It turns out that what is known as string theory makes it possible. So string theory imagines that instead of having these point particles, the world is made up of little strings, little loops of energy, and they can vibrate in one way or the other. It's like a violin string. You can either get one note do, re, mi, fa. If it is do, then it's a graviton. If it is a re, it's a photon. That's roughly the idea. And that makes it possible to connect these two completely different phenomena. So electrons and photons, this is like I'm showing how physicists think about it. Some electron is coming and it is emitting a photon, then it is producing some pair of electrons and positrons. Whereas gravitons, they look like this. And of course, from these pictures, it's not clear, but this is very different. This kind of diagram is called Feynman diagram. It has a very different behavior for gravitons than for electrons and photons and all other particles. Physicists basically scratching their head for 50 years and didn't know what to do. But what happens in string theory? In string theory, each of them is really like a little string. And it is coming in, electron is coming in, it is like a note do, and then it merges into a photon, which is like a note re, and then it's doing something and it comes out. If it is oscillating in a different way, it will look like a graviton. So basically, both these diagrams are actually, again, it's unification, part of the same reality. They look identical when viewed from this higher point of view. So string theory unifies electrons, photons, and gravitons. And that's why everybody is so excited about string theory. But it gives you a very natural way of understanding how unification can happen also with gravity. And in fact, string theory requires you to have gravity. You cannot switch it off. String theory automatically, it's inevitable that you have gravity. So I'm going to give you an analogy. It's a bit like, you have a mechano, right? This is like a mechano, and you have Lego blocks, and you don't know how to connect the two things. But string theory is like these little screws that allow you to connect the two things. So I gave you an analogy of the temple before, and this is another analogy, that you have two different kinds of tools. And if you find the connecting screws, then you can actually combine them into a bigger whole. Is that part clear? Now we will come to Stephen Hawking. Stephen Hawking actually visited Bombay 20 years ago. In fact, I was one of the people who had invited him when I was at Tata Institute. It's a very major school when many famous physicists came together and Stephen Hawking came. And his work has been inspired a lot of work from many of us. And the idea was quantum black holes. Okay, he discovered that this event horizon that we talked about, this one-way surface that you can fall in, is actually such that it's more like a hot metal, and some radiation is coming out of it, and that's known as Hawking radiation. So he did some very precise calculations to show that the black hole actually is hot. Okay, it's not black really. It's like a piece of metal which is emitting radiation. But you know that anything which is emitting radiation means that there are some bits, qubits, some basic fundamental atomic elements which make up that body. Like this room is hot at room temperature. Why? Because there are all these little atoms going around, jiggling around. If you raise the temperature, if you put a heater, what will happen? These atoms will start moving faster. So depending on how many ways these atoms can arrange themselves, you can actually make a connection with the temperature of that object. And also there is another more refined concept called entropy. But this basically tells you how many ways you can, how many bits of information you have in that system. And Hawking's work showed something very spectacular about a black hole. The black hole is as though all the information of a black hole is stored on its horizon, on a surface. It's a bit like in this room, all the information is stored on the walls of this room, not inside the room. So what is happening, you and I talking, is somehow all that information is stored on the walls of the room. So this is actually very counterintuitive, because normal matter doesn't behave like that. Normal matter, if you want to describe how the matter is behaving here, you need to have one bit of information at every atomic length, at some unit. If you divide this room up into small bits, you will need a qubit at every site, which is proportional to volume. But black hole is such that the bits are actually stored, ones and zeros are stored on the surface of the black hole. This is what is really funny about the black hole. And now the question is, how many qubits does a black hole have? Okay, this is a question that you can ask. And basically, there was no answer known in Einstein's theory of relativity. Einstein could not provide an answer to this question. But in string theory, for some class of black holes, you can actually do the counting. You can literally count how many qubits are stuck on the surface of on the horizon of the black hole. And surprisingly, the mathematics for doing that counting takes us to this great Indian mathematician, Ramanujan. You want to count the qubits of a black hole, which is the work that I have been doing. It relates to some very deep mathematics that Ramanujan invented 100 years ago. Okay, and I say it's a deep mathematics, but as you know, as sometimes very deep mathematics can be stated in simple words in high school mathematics problems. So this is a problem for you. Okay. So suppose I give you any integer like 3. How many ways can you write is in different partitions, like 1 plus 1 plus 1, right? Then write as 1 plus 1 plus 2 plus 1 or 3. Right? There are only 3 ways. I'm not allowing you to use minus, only plus. You can only, otherwise there are infinite ways, right? Then you can write 2 plus 2 plus 2 minus 4, like whatever, plus 1. No? So now if you put 2 colors, becomes 1 plus 1 plus 1 green, 1 plus 1 plus 1 red, 2 plus 1, 2 plus 1 red, green, like that. There are 10 ways. If you now increase to more colors, and what Ramanujan did was he gave a beautiful formula for doing this counting. Now you might say, what does this have to do with black holes? But it turns out that there is this connection between the black holes in string theory and Ramanujan's mathematics. And so this is the power of this unification of ideas, you might say. So unity of science. But there is Hawking, working, he's a British, working on black holes, which were written by Einstein's equations, who was Swiss, German, Ramanujan coming from India. All these ideas somehow come together. And there are completely unexpected links between quantum black holes, this gauge theory that I told you about, number theory. This is really the power of science. So now I'm going to switch to why science is important in your daily life, right? So all this sounds very fancy and beautiful, which it is, I can tell you. It's really exciting to work at these frontiers. But now let's come back to the real world, come back to the ground. No? So now, I want to tell you scientific temper in the age of unreason. No? This is Age of Reason was a very famous book written by Thomas Paine 200 years ago, 250 years ago. That observation and logic is a reliable source of knowledge rather than something that is written in the scriptures or somebody that is given to you by the tradition. This is a very fundamental principle of science. And these are the ideals of enlightenment. You dare to know, you challenge authority, you think for yourself, individual liberty, tolerance for other people's ideas, separation of powers of church and state. And some of these principles became very fundamental to later developments. And that actually spurred the scientific revolution. And it's because of that scientific revolution, this is all happening in some abstract world of philosophy and theoretical physics calculations. But everything that we know, atoms, as I've explained to you, cells, biology, planets, black holes, really from the quantum to the cosmos. This is like quantum, this is the quantum computer, cosmos. Now we understand with very simple principles and very simple equations. And this really has led to the age of science. Age of science is really, advances in basic science have led to a rich harvest of technologies, completely transforming our lives. From semiconductors, lasers, antibiotics, vaccines, computers. And we use it very regularly without even thinking. You don't think that in my phone, Maxwell is somewhere sitting over there. And Einstein and some quantum mechanical people are sitting over there. Because transistors would not be possible without all this, very abstract mathematics and physics. At the same time, we live in this world when people have all the conspiracy theories. They think that, no, science is something Western. There are all kinds of misunderstandings about science. Science is not real. So that's why I have called it Age of Unreason. Paradoxically, we also live in the times of anti-science philosophy. Alternative facts, you might have heard this phrase, you have your facts, I have my facts, we both agree, we are happy, right? Anti-vaccines, people now, in advanced countries, people don't want to take vaccines, which is during COVID, we saw that. In India, there was no problem, nobody protested. But in some countries, there was, very strong opposition to taking vaccines. Saying that, no, who are these experts telling us to take vaccine? We did a Google search and Google doctor tells us that there's no need for vaccine. Whatever, I don't believe in vaccines or it causes autism. But climate change, no, it's not happening. There is scientists are saying that it is happening, but I don't believe. I don't believe the scientists, these are elites. So, and there are variants in India. So this is not abstract, but it's a very real world harm can follow, because if you don't respond to the climate change, or if you don't take vaccinations, it actually people can die and humanity can suffer. So it's a very important point, not only to think about the abstract aspects of science, but about the scientific temper, how to think about science. And this is a very nice quote of this biologist. The real problem of humanity is that we have Paleolithic emotions, meaning emotions of like people in the Stone Age, that we get upset and then we start throwing stones at each other, go to war, you're seeing. Medieval institutions like a nation state, my country is better than your country and you want to go to war. But God-like technology. At the same time, we are able to think about black holes, atoms, and all these wonderful things and make these amazing detections, amazing equipment. So we, the descendants of monkeys have this strange thing that we have inherited from our evolution. But on one hand, we are godlike. And on the other hand, we are really like a lizard. We are thinking that, I'm upset with you now. We are going to now go to war. So part of my talk is to really explain to you what the scientific method, why it is so important, why it remains and we should not actually, your generation should not actually get, should actually assert the importance of the scientific method, because otherwise we have to deal with all these problems that are going to hit you. Climate change is going to happen in the next 30 years. Suddenly you'll have a fire, and very, not enough rain, or too much rain, and you cannot deal with it unless you try to understand the science. This is a crisis in the trust of science. Science is seen as something that corporations do for themselves. It's just a construct. The scientists really don't understand. They are just like a club. They come together and say, okay, from today we are going to believe in electron. Tomorrow we are going to believe in a black hole. It's not actually like that. There is enormous amount of work for hundreds of years of thousands of scientists before they actually believe in something. So science is all Western. We don't need it. Indian civilization is different. Science is already in the scriptures. Everything that you are discovering today was already there, either in the Quran or in the Vedas or in the Bible. The scientific temper is we really need this anti-science attitude is particularly damaging at the grassroots levels, because if somebody, a snake bites them and they say, no, I don't believe in science, I'm going to take him to the tantric or mantrik, then the person is going to die. This is what Pandit Jawaharlal Nehru said, that the scientific temper is the temper of a free man. So he realized that science is not just for scientists, but it's really important. It has social consequences. If you want to have development in your country, you want technology, you also need science. And he thought of it as a civilizational problem. Our entire civilization has to respond and change its way of thinking, the scientific way of thinking. That's why our constitution considers it our duty to cultivate the scientific temper, humanism, spirit of inquiry and reform. But at the same time, it does not attack you to say whatever you want to believe in your personal life. So liberty of thought, expression, belief and worship is also guaranteed in our constitution. It's important to understand that our constitution is very, formulated in a way that it does not encroach upon your personal liberties, but it is telling you that, adopt scientific temper. Now, I just want to tell you very quickly about some work that Andhashraddha Nirmoolan Samiti in Maharashtra, you might have heard about it. They fought for a law against black magic. Okay, now you might say, who cares about black magic? We are in the 21st century. We are talking about black holes. We are talking about the Higgs boson, right? But I will tell you that actually this scientific activism is really needed. Because, okay, so I think this maybe I can skip. This part I will skip. The main point is that one charge against science is that it is something that is Western. Okay, this is not our in our civilization, but this is actually so untrue because some of the very great advances in science have actually come from India. This is Brahmagupta or from other parts of the world. Al-Khwarizmi, who was in Persia, and this is Euclid. Everybody knows about Euclid, right? Euclid's geometry you have studied school. Two parallel lines don't meet, there is a triangle, Pythagoras theorem, this theorem, this angle, that angle. But Euclid was really one of the great minds who started to think in this axiomatic way. He said, okay, I start with some very simple principles and then I can derive everything. But Brahmagupta was an equally great mind. So was Al-Khwarizmi, whom you don't know so much about. Then Brahmagupta in the 7th century discovered the idea of a zero. Okay, now you might say, what's the big deal about a zero? You see, everything on your phone works on ones and zeros, right? You write numbers in the binary, it's ones and zeros. Try to imagine if you have a number written in Roman numerals, like 57 times 13. Write it first in Roman numerals and then try to multiply the two things. You won't be able to do it. But now 53 times 13, you can probably almost do it in your head. You can certainly do it on a piece of paper. And even a school kid, you can do it, right? 57 times 13. Can calculate. No? In the past, big Roman mathematicians would spend days to calculate how to multiply. So this is a very big invention of human mind. But also, he assigned some rules about how to add a zero. He really gave zero an identity. It's like a number like any other number, 1 and 0. And this is really foundational to modern mathematics because this is known as modern language is called as the number field. Idea of a number field is not possible unless you have a notion of a zero. And Al-Khwarizmi, you have seen algebra, right? You probably have you done algebra in your school? Not yet. Not algebra yet. But you write, okay, I don't know how many number of if I have some number of apples and if I add 5, I get 8. Right? Also, Bhaskaracharya did this to Leelavati. How do you find how many apples did I have before? How many flowers did I have? Well, you write an equation, x plus 5 is equal to 8. You take this 5 on the other side, you subtract 5 from both sides, and you say x is equal to 3. Okay? This, we take it for granted again. This is like such a simple tool. We think, oh, this is obvious. But this was a very major invention by Al-Khwarizmi. And everybody, you have heard this word algorithm. It actually comes from Al-Khwarizmi. When it went to Europe, Al-Khwarizmi became algorithm. So algorithm means what? Method for you write an equation and you do the same thing on both sides and repeat it. And you can slowly make it simpler and simpler. And then you find this quantity x that you wanted to find. This actually was the basis. Now, with this, we are able to write down the equations. You see, I wrote down Maxwell's equations. But what is this notion of equation? There was no such thing called equation. If you go back at the time of early, early mathematics, they didn't have this notion of systematic notion of equations and doing something to it to solve it. So this makes modern mathematics possible. And you know the word algebra, it actually comes from Arabic because he wrote a book called Al-Jabr wal-Muqabla. Wa means and, like we know. Also in Marathi you say wa means and, right? Al-Jabr wal-Muqabla means restoration and completion. So you restore, you add the same thing on both sides of the equation. And that became algebra when it traveled to you. So this shows that knowledge comes from all over the world. And therefore, we should be open to treating knowledge as a common heritage of all humankind. I very quickly want to tell you now this Black Magic Act that I told you about. This was done to bring social awakening and awareness in society. I mean, why scientific temper is important? Okay, it's not just something for physicists to worry about in their laboratories and their offices. It really touches upon your lives, and you have to be as citizens aware of what is scientific temper. And we quoted Nehru, but actually, how does it actually play out in your real life? So some common criticisms of this law is that why do we need a black magic law in Maharashtra in 21st century, right? How do you know something is a superstition or something is a fact? Is this law anti-Hindu? Is it really targeting only Hindu religious practices? Is this law against our, our indigenous spirit of Swadeshi? These are really agents of West. Why don't we just follow the Indian Penal Code, which is now Bharatiya So this law has some very specific provisions, and practice and propagation and promotion of these acts that I will say, they become punishable as a cognizable offense, a non-bailable offense. And this actually made a big difference, and as I will illustrate. So cognizable means that if it's like a robbery, the police doesn't need a warrant. If somebody is performing these black magic acts, police can come and interfere and arrest you. And then once you're arrested, you don't get the bail. So it has very specific schedule, okay? Like claiming to perform miracle surgery, like just with fingers. This, you might think, who does this? But actually, there are people who perform these surgeries in hundreds, sitting in a daroga, sitting in a temple. It doesn't matter which religion, or in a church. And people are paying money for them. Even that is okay, but if somebody has a serious appendicitis or some other heart, this thing which requires serious surgery, just by somebody putting hands on you and saying some mantra or saying some thing from a Quran or Bible is not going to help you. So this is forbidden in this law. If somebody is found to be doing this, they can be punished. Claiming to change the sex of a fetus, as you can imagine, this is a big thing. That okay, I will just do something and your daughter will turn into a son, for example. Discouraging treatment for snake or dog bites. And just to show how useful this law has been, more than 2,000 cases have been registered. So many godmen and women of all religions have been reported. 20 cases of human sacrifice have been. So you might be surprised, but in Maharashtra, 20 cases of human sacrifice were reported and stopped because of this law, which could not have been stopped otherwise. Because the supernatural fraudsters who come, they are clever. For example, there is this, one of the provisions of the law to somebody making a false impression that I'm an avatar of some god. So what are you doing? You are exploiting the religious sentiment of somebody because they worship maybe Krishna in good faith. And you present yourself as an avatar of Krishna. Now you might say that, okay, come on, sounds outlandish. But actually, there was a person like that who was arrested. First thing that happened after this law was arrest. And he just here in Mumbai, actually not far from here in Mumbai. And he was basically walking in and out of the house. There was a wife and a young daughter whom he was exploiting because he's out. Now can stop him. Then he took 9 lakh rupees and some gold from them. And he could not have been arrested using normal penal code because what is the crime? He says that, no, I didn't give them I didn't sell them in a car which is not working. I just told them that I'm an avatar of Krishna. They believed in me. So, legally it is very difficult to prosecute. So this law shows that this can be prevented. So this is an example of how scientific temper actually is really should be part of your life. And you should be aware of the work that some grassroots level people are doing, or thousands of activists are still working on this. So also you could get involved in their work. But generally to have this awareness that somebody is saying that, Rahu Ketu, now we know, as said, Newton has predicted how the planets are going around the sun. So how can these things which these are not even planets, affect your life? How can Mars, which is just a planet, suddenly become a major problem when some marriage has to happen, right? So these are the kinds of questions that this law forces you to think about. Now I will very briefly in last 2 slides tell you about the center where I work, where we work on this aspect of science at a different level. I said scientific activism at multiple levels. One is really at the grassroots, which I have explained, but also at the level of individuals, also at the level of individual scientists, and at institutional level. So what ICTP does, this is how ICTP was, this is in this beautiful place in Italy, right next to the sea. This is ICTP. We just celebrated our 60th anniversary. And what we do at ICTP is to join forces to unite the world. Because we welcome 200,000 scientists from all over the world. We have in so many years. 200,000 scientists from all over the world, 188 countries. I've been to ICTP. 67% from developing countries, from countries in Asia and Africa, fully funded by ICTP, so that they can participate in the most advanced physics or scientific conferences, talking to the best people in the world. So a student in Ethiopia can talk to a Nobel laureate from Italy. This can happen at ICTP in their field. And we have contributed to many breakthroughs in science, including to 5 Nobel Prizes. So we are really an international hub for science. And this is another aspect of the scientific temper, so to speak, because these scientists who go back to their home countries in Africa, they are basically taking the spirit of modern science with them. They are going to create a scientific community. So ICTP is playing this role from the other end, whereas we also need this grassroots work, and hopefully one day the two things will meet. So we have a unique vision with excellence at the frontiers of science. Global inclusion. We really want to include everybody, whether it's a man or a woman, African or non-African, or Asian or American, and cooperation through science. This is the vision of our founding director, Abdus-Salam. He was a Pakistani Nobel laureate. This quote I like is, "Science creates the common heritage of all humankind." And the important thing is that it's a creation of all humankind. It's not only that we are consuming something that is created by the West. As I showed you, Brahmagupta or Ramanujan, these are examples which show you that the highest caliber of science comes from different parts of the globe. ICTP was at the United Nations recently. And again, there were several examples. The student from Ethiopia who's now studying at MIT. She's from Cameroon. She has become an entrepreneur, and she's in, here is one of our students who became a minister back in his home country in Lesotho in Africa. So we have all these activities all around the world. So in a way, we are sort of spreading the light of science, and think of ourselves as the lighthouse for global science. So this is where I was. Thank you.
Thanks a lot, Atish. Okay, so before we just take a very quick break for chai, let's get the online questions done, because then we will stop the live stream. So maybe I'll go backwards. So one question is, why is scientific temper so less in India compared to foreign countries? And it starts at the school level, where in our country there is an immense potential. We are doing good, but we can do better.
So I don't know if it helps to say that your neighbor is as bad as yourself, but I can say that the problem of scientific temper is not particular to India. I mean, perhaps it is worse in India in certain ways. For example, I think more than something like 30–40% people in America believe that the world was created 6,000 years ago, because that's what is written in the Bible. So many people in Europe still don't believe in the fact that the climate change is happening. They don't want to believe in it because it's uncomfortable. Because then you may have to cut down on use of energy. There was huge opposition to vaccines. So I think the scientific temper is really needed in all countries, I would say. But I think in Europe, during this Enlightenment period, I told you about the age of reason, there was a lot of churning that happened in the society for 200 years. And there were many struggles that happened. Like people like Bruno were burnt at the stake. It did not just come about this grip of all the, the old mythology was not broken easily. And it took efforts over decades or even a century. So India became independent recently. So I think it's not, one should not be expecting that the problems of creating a scientific temper is a 3-year project or a 30-year project. I think we have to keep it in mind as a civilizational project, as Nehru stood.
Why does culture get the steering wheel over critical thinking in India?
I mean, part of the reason is that,
being looked down to it.
Yeah. no, I think part of the reason is that it is, has to do with this notion of Swadeshi. And I think it's a misunderstanding that somehow modern science is foreign to us. The scientific method is something that doesn't exist in our society or in our religion or in our philosophy. This is not true, because if you look at actually Rig Veda's Nasadiya Sutta, it really expresses this kind of similar kind of a scientific wonder. Where did this world come from? Who created it? Is there a God there? Maybe there is a God, maybe there isn't. So it's kind of agnostic. It's trying to understand. Or if you look at the Lokayata tradition of India, it questions even, is there even a God? I mean, it says that there is no God, there is no soul. So India has this, diversity of traditions in our culture. So there is no reason to really think, if you interpret it correctly, that being Swadeshi does not mean that we reject this modern knowledge, but we actually can make sense of it in the context of our own history and own philosophy. And that is really the challenge that we have. We need to celebrate people like Brahmagupta. I mean, there is also colonial legacy that we have learned about Euclid, but we have not learned about Brahmagupta in our own country. Now people are realizing, but at the same time, we don't want to create mythology into science. Poetry and mythology is one thing, science is another thing. So we cannot say that everything was known to Brahmagupta. Brahmagupta made some major advances, but then other scientists came from other countries. There is no reason to have this sense of inferiority that India cannot create great science.
Okay. There are two questions from the earlier part of the talk, which I will just put together. How elegant is the mathematics of string theory? Without experimental evidence, can we rely on the elegance of the mathematics as confirmation of the theory?
So one of the reasons why you continue to do string theory is because of this very elegant mathematics and this very natural unification of forces that happens without you having to put into it. But I think it's a very good question, because no real physicist believes that a theory is confirmed unless there is an experimental evidence. Even those of us, including myself, who have spent a good part of their life working on string theory, would not just, that would be superstition, okay? If you just say that, oh, no, I believe in string theory, nobody can tell me that it's so beautiful, it has to be right. Nobody says that. We are at a different point the Higgs boson, which I mentioned, most leading scientists believe that the Higgs boson must exist. Okay, something like a Higgs boson must exist. For 50 years, and a big experiment was planned based on that belief, right? Otherwise, without that belief, who would give you 1 billion euros to construct this huge machine, right? This was done because scientists really believed in the equations that they were writing down. They were confident based on the power of those equations, because they were able to explain light, they were able to explain all these phenomena. So they believed that with these equations are telling us that there must be a Higgs boson. But nobody in their right mind believed in the Higgs boson until it was actually found. And how was it found? Enormous experiment, huge experiment with thousands of people, and the confidence level had to be 1 in a million. Like, people were willing to bet 1 to a million. That was your confidence level. That you're seeing the Higgs boson million times instead of, and maybe once you don't see it where you want to see it. So that's the level of confidence when you believed in the Higgs boson. So similarly for string theory will not be accepted as a theory of nature until there is a clear experimental evidence for it. But we continue to work on it because it has a very strong, logically consistent structure, which is very compelling.
Great. Thanks. I think there is another question, but that's a very good question to take over chai. So this is a good time to break and go for chai. And that question is, why do the Vedas have the answers for things only after a scientist discovers? Okay. So on that note, we will stop the live stream. Before we do that, just a reminder that there will be a third and a fifth Sunday Chai and Wine in March, and a month from here we will be talking about chemistry.
Yeah.
Okay. On that note, let's take a quick chai break here and come back, and we can continue with questions.
So I just want to say that I think Chaire is really a great title.
So go and get
And I'm looking forward to